All right. Thank you for coming, everybody. And thank you for the invitation to speak tonight, specifically Anna and Danny. I'm really looking forward to sharing some of the backstory of the publication, as well as having just a great discussion with all of you as well. All right, so quick agenda for the brief talk. I am going to start with a short about me slide. And then Anna and Danny asked me to come up with some 5 major highlights about the work and about the process of doing the work. So I'll go through each of those. And then I describe this paper as a little bit different. So then I'll kind of talk about my process of thinking through writing and then eventually publishing a paper that's a little bit different. I also just really love PhD comics, and I thought I would share that with you and hopefully make you laugh as we start. This is very emblematic of my grad school experience with this work. I assume I am not the only one that can relate to this on the call. So this kind of just emphasizes the theme of the presentation today. So like I said, first I want to introduce myself. Here is my educational background. Like they said, I'm currently a PhD student in mechanical engineering at University of Delaware. Does anybody recognize that first logo?
Dayton.
Dayton, yeah. So I did my undergrad at University of Dayton in mechanical engineering and minor in human movement biomechanics. If you're anything like me and you went to or are currently at a basketball school, the college basketball season starts tonight. So I will try to keep this quick so we can all go watch our games tonight. In addition to school work and liking college basketball, other hobbies that I have are playing flute and piccolo. I was in marching band and pep band in undergrad. I'm currently in the community band. All that is to say, if you're a student, and even if you're not a student, I highly encourage you to participate in things outside of your research and outside of school. It really builds your network and it's just fun. I also had to throw in a picture of my dog. This is a 13-year-old Bichon named Maddie. So if I'm not playing flute or not doing research, I'm probably playing with Maddie. Depending on how noisy she gets this evening, she may or may not make an actual appearance. And then I am also heavily involved in service. I'm a program fellow for the Perry Initiative. This is an organization that seeks to inspire young women to pursue careers and leadership positions in orthopedics and engineering, which are 2 fields women are highly underrepresented in. Every year, we look for new program fellows to lead these outreach programs across the country. So if you identify as a female or non-binary and are interested in this position, please feel free to ask me questions about that at the end, because I'd love to talk to you about that. All right, so now let's go ahead and get into the highlights. So the first highlight, which was brilliantly described on Twitter by 2 corgis on a treadmill, which I just love that gif, is 100 ways to use a treadmill. So I'd like to start with this because I think even with simulation studies, it's really important to start with the motivation, specifically the clinical motivation for the work. So treadmill gait training is important because it's a common tool for rehabilitation. It's common because it's low cost. You can do it in a small space, and it allows for repetition of motion, which hopefully will lead to some use-based learning. It has also been shown to improve walking function and efficiency, improve symmetry between limbs, and reduce postural instability and increase an individual's self-selected or comfortable walking speed, all of which are positive rehab outcomes for gait training. And then finally, if you push them to walk at faster speeds on a treadmill, you can see increase in propulsion generation with a lot of different clinical populations. This plot here is from a paper showing individuals post-stroke. So there's a lot of different ways to use a treadmill. Just speaking in terms of gait rehab, like I showed on the last slide, simply just using a fixed speed treadmill like you have at the gym, you set the speed, you walk at that speed. Doing that at a fast speed can really improve walking. But one of the limitations of fixed speed treadmills is that you have to walk at that specific speed and the speed's not changing like you can over ground. So it limits some of the natural stride to stride variability that you have. So a lot of researchers, including our group, have been making adaptive treadmills, or sometimes called self-paced or user-driven treadmills, that allow for more of that stride to stride variability. Again, that's not the focus of this work, so I won't spend time going into that, but I do have some other papers on that. So if you have more questions about adaptive versus self-paced treadmills, I'm happy to answer those at the end too. And then finally, belt acceleration paradigms are becoming more used. So this is where they accelerate the belt for the back leg, or called the trailing limb, at push-off, which forces the individual to increase their push-off force so they can maintain their balance. So it's a little bit harder on the webinar format, but I think you can all unmute yourselves. Does anybody have suggestions for other ways to use a treadmill, or ways that you use a treadmill in your research?
You can also put in the Q&A. That should be enabled if you don't want to unmute yourself.
Yeah.
I study turns, and I've seen a couple of papers on people looking at rotating treadmills.
Oh, cool.
I don't know the particulars, but it
Yeah.
seems like it'd be cool for side-to-side stability.
Yeah, that's cool.
This isn't my work, but I saw a study data collection today on that treadmill in the background that was doing gait perturbations, or like trying to induce like trips or slips, which I thought was pretty cool.
Neat. Well, I won't take up too much time, but thank you for sharing. So other suggestions I had, slips and trips was one of them. Combining treadmills with other tools. So in our lab, we have functional electrical stimulation, where you apply some activation or shock to the muscles to activate them at certain times. You can use exoskeletons that apply torques at the different joints, harness systems. We have instrumented handrails in our lab, which are kind of cool. You can measure the forces that individuals are using to push down on the treadmills, and that information could be used potentially to design improved canes or walkers, or maybe figure out how far or how close those should be relative to the person. And then also you could look at how the slope or the angle of the treadmill, if you can incline or decline the treadmill, would affect the way that somebody walks. So there's a lot more than just these. These are just what fit on the slide. I said 100 ways. This is obviously not 100 ways, but you get the idea. Treadmills are used for a lot of different reasons. So my first highlight showcased ways a treadmill can be relevant clinically, but the next question that I usually get is, why did we decide to create a musculoskeletal model and simulation of treadmill gait? Which brings me to highlight 2, which is, why might you want to use musculoskeletal modeling and simulations to complement your experimental studies? So one reason is to estimate values that are difficult to measure experimentally. Some examples of that could be joint contact forces or muscle forces. Not a lot of people are volunteering to participate in studies where they have to have a load cell implanted in their muscle belly or instrumented joint implants. So we need simulations to be able to get those outcome measures. You can use simulations to isolate and test hypotheses that might not be able to be isolated experimentally. For example, muscle weakness and contracture are 2 impairments that often go together. So you can use simulations to kind of tease out the effects of each of those on motion separately. You can use simulations to study how non-human animals move, like dinosaur locomotion. And you can use them to generate lots of data for a wide range of studies that may or may not be possible experimentally. So like injury biomechanics, for example, we can't actually ask our participants to come in and get actively injured during our studies. So you can use simulations for those. We chose to use a simulation for this paper because we wanted to create a framework that could predict speed-related changes in treadmill gait mechanics, which could be hard to do experimentally with clinical populations because that could require long, fatiguing experimental studies. So moving on to highlight 3, let's say now you have a research question that fits into one of the previously mentioned reasons to use musculoskeletal modeling and simulations. Where do you start? So if you're like me, you get excited and impatient when starting a new project, and you see the big picture and you just want things to work, so you want to start at the end. And I assume that I'm not alone here. I see Anna smiling. I think this happens in a lot of different types of studies, but definitely for me with modeling. So as much as I hate to admit it, I have learned during grad school that the best place to start with modeling studies is to start simple. So I have actually found that as much as I think starting at the end will get me to the finish line quicker, it actually leads to more bruises on my head because I'm banging my head against the wall in frustration, not literally. But I've also found that starting simple can actually get you to the end quicker and improve your overall understanding of what's going on. So the best advice that I got when I was doing this work was to actually start with a block on a treadmill. So the novel part of the work, or one of the novel parts of this work, was modeling the contact between a moving treadmill belt and a relative moving body, or ideally the gait model. And so to understand what was going on there, it was suggested that I start with a block on a treadmill and then move to the gait model on a treadmill. So, like I said, the motion I wanted to analyze was gait. So I am not sure how many of you are super familiar with gait, so I'll just give a brief overview of gait. So gait is often broken down into two phases, stance and swing. We focused on the stance phase with the block model because we wanted to specifically look at that interaction or the contact between the foot and the belt, or the block and the belt. So stance is when the foot is in contact with the ground. Swing is when the foot is not in contact. So then specifically within stance, we broke it down into 3 different interactions between the foot and the belt that we decided to highlight. First was heel strike. So that's when your heel first makes contact with the treadmill belt. Next is heel rocker, which encompasses both of those first 2 blocks. So that's when the foot is rotating about the heel. And last is translation of the foot backwards with the treadmill. So we wanted to simulate each of these 3 interactions with the block. So I have videos of each of those simulations. So starting with heel strike, we had the block start 2 centimeters above the treadmill belt and fall on the belt and then translate back with the belt. 2 centimeters I found in the literature is roughly the average distance the heel is from the ground before descending into heel strike. So there you go. That's the first, we'll play it one more time. That's the first video. Hopefully these videos, sometimes videos don't turn out great on Zoom. Okay, perfect. Then we have heel rocker. So same thing, did some research, found that the initial dorsiflexion angle for the ankle is roughly 10 degrees for healthy individuals for peak dorsiflexion. So that's what we started with there. So you can see it rotating and translating back one more time. There we go. And the last one, super exciting. The foot is just, or the block in this case, is just translating backwards with the treadmill. So I don't want to spend too much time on the results like I suggested earlier, but I wanted to stress the importance of doing gut checks, validation with simulations. Even with simple models, it's really important just to make sure it's doing what you think it should be doing or what physics or the laws of biomechanics say it should be doing. So for quick background to understand these results, we did a state tracking simulation for each of these 3 different motions and used that as the initial guess for the predictive simulations. The top row here is the states or the position of the block. And then the bottom row is the ground reaction forces between the block and the belt. So you can see that there's small root mean square errors between the tracked and predicted states. So our states are good. And then our ground reaction forces also reasonably make sense. The one thing that you might see if you were looking at these long enough is that the peak ground reaction force for the fall motion, which is that first column, so the bottom left picture plot, is 8 block weight, which is really high compared to the average 1 or 1.5 that you would see with just gait. But we think that's probably due to the fact that the block is free falling, whereas in gait, the foot is in controlled descent. And also in gait, the weight is typically balanced over both legs, whereas here it is all falling on the one contact model. So our gut check here shows that with the simple model, we got a better understanding of how to modify a gait model to add in a treadmill and make sure that the contact between the feet and belt worked. So this simple model definitely helped us as we progressed. So I skipped over this earlier, but to run the simulations of the block and the treadmill, and then ultimately the gait model and the treadmill, you first have to determine which simulation pipeline is the most appropriate for your research question. So I am not going to go through all of these different pipelines. The purpose of this slide was just to show you there are lots of options. And Elmo agrees, there are too many options. So how do you choose which one to use? And that brings me to my fourth highlight, how to choose an appropriate simulation pipeline for your research question. So the steps that I kind of followed were first to read a bunch of articles. So start with some recent articles that have used the different pipelines that you're thinking. And then also I would encourage you to read some of the seminal papers that are associated with each of those pipelines. You can usually find those on Google or references on OpenSim documentation. It's a pretty great way to find those. So I encourage you to read those first. Then in 2020, I believe, Stanford did an OpenSim webinar on how to choose a simulation pipeline and literally have slides on examples of each of them, what each one is used for, how long each one should take to run. So I use that as an excellent resource. They have the recorded YouTube video as well as the slides available online. So that's a good resource. Then in addition to Google, I highly encourage you to talk to people. So use forums. The modeling community is super friendly. I think several people on here would agree and are excited to answer your questions on the forum and to help you out. And then finally, look through some shared models and code. So I have shared this model and simulation code on my SimTK project page. GitHub is another place to find them. So when you're done, you should share them. And then when you're trying to figure out which pipeline to use, look through what's already been shared and what's been completed before, so we can build up our repository of examples. So I decided to use direct collocation for our study. I won't go through the math or really explain it much, but just a quick high-level explanation of what it's doing. Direct collocation the goal is to generate a motion based on high-level task goals, such as minimize effort, let's say, defined by an objective function that includes those goals. So some pros of using direct collocation is it's fast and you can generate new motions without experimental data. So that second reason is really why we decided to use it for this study, is we wanted to do completely predictive simulations. And then some cons are that it can be difficult to implement because the math can be confusing and it's hard to add in feedback loops. So that first con has actually sort of been fixed by OpenSim Mocha, which is a relatively new tool, open source tool for direct collocation. It is a great tool, but it can still be challenging to use because it is a new tool. So some advice for getting started on using it, that's what we used for our work. Again, be active on the forum. Everybody really wants to help each other. Share questions as well as insights, because your insights might help other people too. I know Evan has been really great at doing that. And then start from provided examples that are available in the download or things that you find on GitHub or SimTK or other sites. We started with the 2D gait example, added a treadmill, worked our way up, added more complexity, and that was a really great place to start. So don't start from scratch if you don't have to. So moving on to the last highlight, musculoskeletal modeling and simulation and a lot of other research areas that you all are in involves a lot of trial and error, which I don't know about you, but for me as a grad student, when I read other people's papers and I see the pristine, finish line of their paper, here's the one equation, here's the model, yay, it worked. I tend to develop some imposter syndrome because, well, they solved it. Why can't I figure out my problem? Why did I have to go through so many iterations? So I often find myself having to take a deep breath and reminding myself that they probably also went through several iterations to get to that final product. And that wasn't their original version. So we definitely have to remind ourselves to do that. But then some advice for when you're going through the iterations. I encourage you to document each iteration and use version control. Use memorable file names, because if you're anything like me, you work on something for a while and then you have to stop and go do something else and then come back to it. You want to remember what file you should be using, what's the most recent version. So use memorable file names to help you with that. And then I highly encourage you to talk and share with others who have been through ruts or going through ruts currently. This is something I'm really hoping to have a discussion about at the end too, ways that we can really redefine this failure of the trial and error in each iteration. From what I looked up this past week, the Journal of Trial and Error is a real thing. I had never heard of it before. And that would be a really cool place for us to publish like iterations of our modeling. And I know I learn from each iteration, but then other people who, I don't sit next to in the lab, sorry, Caleb, that hear me talk about each iteration and why it didn't work, other people in the community don't get to learn from my mistakes or my iterations. And so doing something like this or having some place where we could share that could be really helpful to help redefine failure as learning opportunities for everybody. So if you're aware of those options or opportunities like that, please feel free to share those in the discussion. I'd love to hear about that. And then finally, be patient and kind to yourself. I know it can be really hard when you really just want to get to the end, but as much as you can, do nice things for yourself. And then you can do it. I was so excited when I made this video. It is the culmination of many months of frustration, but being able to say that I did it and created a simulation framework that might actually be able to influence design of rehab interventions one day is a really great feeling. So here it's kind of a combination of 3 different videos: a slow speed on the treadmill, a fast speed. So that's the slow. Next is comfortable, and this last one is fast. So that was pretty cool. And then real quick, again, another gut check here with the gait model. So we were able to show that with increased speeds, they increased peak hip extension, peak ankle dorsiflexion and plantar flexion, and peak propulsive forces. So the outcomes matched what we'd expect with experimental trends. So that was super exciting. All right, so this is my last slide. So like I said, this paper was a little bit different. We focused more on educating readers on our process, or the general process that we took for how to develop and validate a predictive simulation framework for treadmill gait than our results. So if you're planning on writing more of an educational paper, or a paper that you'd say is a little bit different, I have some advice or suggestions that I took from my process. So first, I spent a lot of time up front outlining, drafting, and iterating. I made several different outlines to kind of figure out what is the best way to go about educating on our process. Of course, when I started drafting, that changed, so I had lots of different drafts as well. I also started with the methods, because that was really where most of the education came from, was how we did what we were doing. I read other papers that I thought were a little more educational in nature that helped kind of with the structure and the flow. I tried to think about it like if I was leading a webinar, how that would flow. I asked for feedback from lab members. So this can be really helpful if you have lab members that do similar work to you, but as well as lab members who do different work. Since the goal was a little bit more on the education side, it was helpful to have lab members who are more on the experimental side and not as comfortable with the modeling stuff, so I could get their feedback on, does this make sense to you? Would you be able to read this and understand it? And then finally, I spent quite a bit of time figuring out what the appropriate journal would be. So I'd encourage you to do that too. We ultimately decided on the Journal of Biomechanical Engineering for this paper, because we had seen other studies in there that were a little more educational, like the how do you know if your model is good enough paper. And so we decided that was a good fit but sometimes journals will do special editions that your work might fit into. So I'd encourage you to really think about that on the publication side too. So with that, I am done with the presentation portion. I want to thank the ASB Student Committee, specifically Anna and Danny, for inviting me to lead the AMA today, all of my funding sources, and of course, my lab members for their support. And now I'm happy to answer any questions that you have, and I hope we can have a good discussion.
Thank you, Kayla. That was awesome. I love that you talked about, like, obviously the success of it. And I was reading your paper this morning, and it looks like it was easy and you just, you did the thing, it worked. And so it's very cool. Like, that's why this series is so cool, because we get to hear the behind the scenes of it wasn't that easy. Because I think sometimes when we're writing, we struggle and feel like no one else has all this many issues. So
Right.
Thank you for sharing that. I can start off questions. So I liked what you said about the importance of like documenting and version control. And I'm actually working on something right now that I feel like every day I work on it. And then the next day I have to almost spend like 30 minutes trying to remember what I did. And I've kind of tried at the end of the day, like writing myself a little note of where I left off or something. Do you have any tips for how you would kind of get yourself back in the zone, or like remember what you were doing so that you didn't have to spend 48 hours in a row working on it and you could take breaks?
Yeah, that is a great question. I have definitely struggled with that throughout grad school too. Specifically, like I said, especially if I have done the modeling for, a month or two and then switch over to some experimental data collection and then come back, I totally forget where I was. So definitely I've been doing the notes thing too. I kind of like to keep an Excel doc or Google Sheet or whatever you use to kind of organize the thoughts a little bit better. So with like the model name or the simulation file, or maybe a column for the results, and then why it worked or why it might not have worked. So that's something that has helped me. But yeah, I think it's really personal preference. There's a lot of different ways to go about that. Have you found that the notes, has it helped you at all?
Depends how detailed my notes are. But yeah, I think it has helped me at least remember, like, okay, tomorrow, think about this.
Yeah.
Or this didn't work, but I don't know why. And
Right.
so, yeah, but I like
Right.
the idea of kind of making almost columns, like,
Mhm.
here's what I did. It didn't work because of this. And like,
Here's what I'm going to try next. Yeah.
Thank you. So yeah, if anyone, we have about like 20 minutes for discussion. So you can ask Kayla anything. We can talk to each other. I think everyone should be able to unmute at this point. If you don't feel comfortable unmuting, you can put in the chat. We'll probably have a recorded chat for 10 minutes. Then the last 10 minutes I can unrecord. So if you don't want to be recorded, you can save your questions for then, or put in the Q&A and we can read them out loud.
I was wondering what some of the more challenging aspects of learning Moco were for you, because it's one of those things where like I've seen it and I've seen people do really cool stuff with it, but I've never used it myself and it seems kind of intimidating.
Yeah, that's a great question. I mean, definitely it being a new pipeline, new software system makes it a little intimidating. When I started, I went through and I think I still have it. I made a huge document of like explaining exactly what Moco is used for, like why you'd want to use direct collocation. And then I went through each of the different examples and kind of figured out what each of those was doing. I also went through a lot of the common or the cost terms that they have in there. And I just really spent a lot of time with the documentation. I think their documentation is pretty good. So I have mostly used it with MATLAB, but you can use it with Python or C++ as well. But they have a whole common functions for MATLAB document. So I've used that too. So definitely starting with an example. If I had to start from scratch to do a problem, I'm still not sure I'd be super comfortable doing that by myself yet. But definitely starting with an example and building from that is really helpful. Yeah.
And maybe as a follow-up, one thing I always get caught up in with Moco is like, how deep do I need to understand the like transcribing the equations and discretizing things? Like, how far down the rabbit hole do you let yourself go before you say, okay, like that's far enough?
Yeah, that's a good question. I think it really depends on the research question that you're trying to answer and what exactly you need to do. So for example, for my last project, I need a cost term that's not available in Moco yet. So I am trying to go a little bit further to figure out how to write my own or work with them to figure out how to write it. So I have to go a little bit deeper there. So I think it really depends on what you're trying to do.
I haven't had to transcribe any equations though.
Yeah.
That's sort of the point, as I understand it, of leveraging the OpenSim environment.
Right.
But there's certainly things that it doesn't do, and they might even be things that your advisor says that it should certainly be able to do. But that doesn't necessarily make it do those things.
Yes, absolutely.
And it has its own forum, if nobody has said
It
that
does.
yet. The Moco forum
Yeah.
is separate from the OpenSim forum, so it's very streamlined to read and find stuff.
Yeah, and they're really good about responding too. So, yeah.
Had you used Moco before? I guess I'm wondering, like, if a student is new to like a programming language or a modeling software, how do you even kind of get started in learning how to use it?
I had not used Moco, but I had used OpenSim. So that definitely helped because I was familiar with kind of their documentation, and a lot of the Moco documentation is set up similarly. So definitely getting yourself used to the documentation is important. And then again, I really think going through the examples. So if you've never used OpenSim before, OpenSim has lots of tutorials that take you step by step for what buttons to press and how to get outcomes for different studies or research projects. So I'd highly encourage you to go through those tutorials. That's how I started with OpenSim. Moco does not have, to my knowledge, those kind of tutorial setups yet, but they do have lots of examples. So when I started, I knew I wanted to use it with MATLAB. So I literally went through all of the different MATLAB examples and tried to kind of understand what they were trying to do in each one before I even started doing my own work. So that's where I would start.
And I have another question on the topic of OpenSim. I have not used it ever. I do, just experimental work, but I'm curious, like, I'm fairly comfortable in MATLAB, but how well does OpenSim like share its data, excuse me, like share its data with MATLAB or whatever programming language you're using? Like, if there's something that you want to do, like you were saying that OpenSim doesn't do, is it terribly difficult to try to figure out a different way to do it, or are you kind of just stuck? How does that work?
Yeah, there's a pretty good API between MATLAB and OpenSim. And then again, lots of examples online of users using MATLAB. Also, again, the forums are a great place. I have found lots of lines of code from other people in the forums that I have just been able to plug and chug into my MATLAB code to help me. So that's kind of where I've started with that.
Thank you.
For almost everything, if it doesn't work through the MATLAB API, it doesn't exist in regular OpenSim either. So you're stuck building it in the source code. Either way, it's not like you're being locked out of something by doing it in MATLAB instead. It would be
Could you comment more on the computational power needed for running OpenSim Moco? How much time did it take or something like that?
Yeah, so one of the pros that I suggested was that direct collocation is fast. So another method that individuals have used for predictive simulation is shooting methods, and those tend to take longer because they run each kind of step one by one, whereas direct collocation is running each step at the same time, so it is going faster. It really depends on your question and the complexity of the model and the cost function that you're using. But mine is running now in less than an hour. So it's going pretty quickly. And then I can run it just on a laptop, so you don't need a ton of computational power either. I mean, the laptop fan starts to spin a little bit quickly, so it's nicer to run it on my desktop at work. But you can do it definitely if your model is not super complex. Again, in this study, we're just using a 2D gait model, so we're not getting too terribly complex, so we don't need a ton of computational power there.
When you're going from
super. Oh, sorry.
Oh, Danny, go ahead.
Talking, Anna. I can't hear you, Anna. Okay, all right. Super basic question. You talked a lot about kind of the steps and your tips and tricks, which is super helpful. Thank you for that. If you were to go back and do it differently, is there anything that you wouldn't have spent so much time on, or you would have spent more time on, or just something that you think you would have done differently?
Yeah, that's a good question. I think I probably would have asked for help sooner. There were a lot of places where I was metaphorically banging my head against the wall and just frustrated. And I just kept trying to figure out what I needed to do next. And as soon as I typed a question in the forum or I sent an email to the folks at OpenSim, they would send me the one line of code that likely I was not going to figure out on my own. And it solved everything, and my simulation automatically started running. So I would say that if you're stuck and have been stuck for several days and you kind of have an explanation for why it may not be working, it is okay not to wait a month or more. Go ahead and ask your question.
I'm stuck right now, so that's good advice. I need to just get over it and ask. Thanks.
They also will just copy the link to a forum post if you can't find it because it's too far in the past. So like there really are, that's the most like you asked a stupid question it'll like get, and even that they'll do respectfully. So like it really is fine to ask any questions.
Right. Yeah, the community is so nice. So.
So another question for you, Kayla. Kind of two questions. First is like, what's next in this research? Because as we all know, we always just end up with more questions than answers, right? And kind of going along with that, how did you decide where to stop this project? Like, how did you decide that I have enough to publish, and you know what the story that you're trying to tell is? Yeah,
that's a great question, or two-part question. So what we were trying to do when we set out, so I talked about the adaptive treadmill a little bit earlier. So experimentally, a previous student had found that individuals post-stroke walking on the adaptive treadmill, some of them responded or increased their speed and increased their push-off forces compared to a fixed speed treadmill, and some of them did not respond. And so my dissertation research is kind of figuring out how we can customize or modify the adaptive treadmill to specifically target individuals' specific impairments, to promote each individual to be able to respond to the custom adaptive treadmill. And so this is kind of where the simulation comes in. You can't necessarily have them walk on 20 different iterations of an adaptive treadmill. Or if we were to develop an adaptive treadmill that was able to change with like human in the loop optimization, let's say, that can take upwards of like 20 minutes or more to converge. You just can't have an individual post-stroke or with another neurological or musculoskeletal disorder walking on a treadmill that long. And so that's kind of where the next step is. We are working on modifying this framework to simulate the adaptive treadmill, so that we can have an initial guess. Obviously, simulations aren't perfect. They take, you can't include psychology or other factors that are present experimentally, but ideally it would give us an initial guess that we could use to kind of have a closer place to start with what version of the adaptive treadmill would be best for an individual, and then go from there experimentally so it wouldn't be as fatiguing for that individual. And then your second question was, how did I figure out where to stop? When I was able to get that video that I showed that looked like physiologically reasonable gait at each of those different speeds, and the different kinematics and ground reaction forces that were reasonable, we were excited by that and decided that was good enough. I tried to scale the model, but at the time, MoCo didn't allow for scaling of the muscle model that works for MoCo with direct collocation. So I spent, I don't know, at least a few weeks on that, and then figured out that MoCo did not work with scaling. So then I just decided to go with the generic model, see if that worked, see if I'd get reviews back that said I needed to try to scale to compare with experimental data, and didn't. So that worked out. But yeah, that's definitely a challenge. It's figuring out where to stop and submit. But if you think you're close enough, I would say go for it. If your advisor tells you that's good, go for it. See what the reviewer says. And then if you need to make modifications based on that, for sure.
I am going to stop recording.